Okay, students, so we are in video lecture number 14 and we start with reactions, types of reactions. Yeah, but it is related to, as always, it's related to metamorphic reactions. So now, the important point here to consider is, you have a system where you have a G system, which is a rock for your case, is equal to sigma Ni Gi, where Ni is the number, I is equal to 1 to N. So what is N? N is the number of moles of a particular mineral, and Gi is the free energy of that phase, free energy of that phase, G solid solution at a particular pressure temperature condition of that particular phase. So this is the summation of the minerals Ni into Gi of all is equal to the total free energy of the system, or in this case, your case, it's rock. So what happens if you have reactions? What happens is, when does a rock re-equilibrate? When the free energy of the rock becomes a minimum at a particular pressure and temperature condition. So you have what is called del G system. If there is a minima and it is dl and I, then this should be equal to 0. As you know from your class 12, maxima and minimum. So the first condition that it should make is del G system with dl and I is equal to 0, which means sig del of this by dl and I should be equal to 0. That is the first condition. And the second condition is del square G system divided by del Ni squared. This should be greater than 0 for the minimum. Right? So we are in this case that you have a system and it is a chemical system. It has some chemical composition, and you have to equilibrate the rock with respect to certain minerals, and that should be done for condition 1 and condition 2. In other ways, there should be some metamorphic reactions. If you have a particular rock at a particular pressure temperature and you want to change due to some tectonic processes, that pressure temperature condition needs to be changed into another pressure temperature condition, then the rock now re-equilibrates to this new environmental conditions. In doing so, that particular chemical system now reactivates itself, and it tries to find out the mineralogy. Mineralogy means the number of minerals or the number of moles, and the composition of the minerals, and the proportion of the minerals, so that the total free energy is equal to, the first derivative of the system is equal to 0, and the second derivative is greater than 0. That is the precondition. So, in a rock, for example, which has, say for example, you have a rock where you have several minerals, say A, B, C, B, C, A. So, you see at a particular pressure temperature condition, you have the minerals, these number of moles of A, these number of moles of C, and these number of moles of A, at a particular pressure temperature or environmental conditions, as it is called. Now, if you change that condition due to certain tectonic processes to another tectonic process, say for example, in that rock, there will be mineralogical changes so that the total free energy remains minimum. So what will happen? A lot of reactions will take place, or some reactions would take place. Even if some reactions does not take place, the phases will exchange reaction so that the thermal equilibrium is approached or better attained. So obviously, when a rock changes its mineralogy, the basis of metamorphism, you know from your metamorphic phases principle, a particular rock for a particular pressure temperature will give you the same minerals. If there are several types of rocks for the same pressure temperature, they give you different sets of minerals. It is because of this very constancy of the whole thing that is very important. That for a chemical system, if you change from one pressure temperature to another pressure temperature, then the rock has to attain the minimum free energy. In doing so, it has to change the number. First of all, G has to change because it's a change of pressure temperature condition. And then the Ni of the mineral has to change its pressure temperature condition. So two things need to remember here. Gi is equal to G0 plus RTLN activity. Remember, in the activity you have mole fraction into the activity coefficient. So when you minimize it, you need to change Ni and Gi. Gi because it's a function of pressure and temperature, and because it's also a function of composition. So it's a very complex situation. When you change the tectonic process, change the pressure temperature condition of a rock from one to the other, then the rock, in order to equilibrate, has to have a minimum free energy. To have that, the first derivative should be 0, and the second derivative should be greater than 0. In minimizing this system, therefore, all these parameters have to be changed. And if they have to change, then either there should be reactions, or there should be change of compositions, or there should be both to achieve that free energy minimization at a change condition. So then, now what I want to talk to you about, if this has to be done, what are the types of reactions that are available? What are the types of reactions operate? And many of these reactions operate sometimes simultaneously, sometimes sequentially, and there are many types of reactions. So you can divide the reactions into essentially two parts. One is fluid-free reactions. Fluid-free reactions. Those reactions that do not involve any fluid component. Do not involve any fluid component. And then there are fluid-bearing reactions. That means reactions in which a fluid component is inbuilt in the reaction. Say, for example, the fluid-free reactions. Say, for example, the first thing that appears to you is polymorphic transformations. Polymorphic transformations. These are the simplest of them all. Polymorphic transformations. Alpha quartz to beta quartz is one type of transformation. You know there are two types of transformations, polymorphic transformation. One is called reconstructive transformation. Reconstructive. And the other one is called, what is it called? Yeah, I forgot. Getting old. So there are two types of reactions. In one, I forget it. Anyway, there are two types of polymorphic transformations. One is something like alpha quartz is equal to beta quartz, such type of reaction. And the other one is like sillimanite equal to kyanite. This type of reactions occur. These are the polymorphic transformations that occur. Second, another type of reactions are phase breakdown reaction. Phase breakdown reactions. In these reactions, the minerals to the left and the minerals to the right, they are not same. The mineral components, the minerals to the right and the minerals to the left, they are different. Say, for example, CaL2Si2O8 dot CaCO3 is equal to 3CaL2Si2O8 plus CaCO3. This is calcite, this is anorthite, and this is a mineral called meonite. This is a meonite. It belongs to a group of minerals called scapolite. In the mineral formula that I have given you, these names are all there. So this is a phase breakdown reaction where a phase meionite, which composes 3 molecules of an anorthite and 1 calcite, this is a mineral by itself, and it breaks down to 3 anorthite plus calcite. So this is a phase breakdown reaction. The minerals on the right hand side of the reaction and minerals to the left hand side of the reaction, they are not same. So you have polymorphic transfer. They don't involve fluids also. You can see there is no fluids involved. There are many hundreds of examples. I've just given you one, for example. So you have, say for example, another very simple reaction is Al2SiO5 is equal to Al2O3 plus SiO2. So, say for example, this is sillimanite, this is corundum, and this is quartz. So, these are all examples of phase breakdown reaction, but they don't involve any fluid species. So, we have one is polymorphic transformation, one is phase breakdown reaction, and the other one is called exchange reactions. Exchange reactions. These are where the phases on either side of the reaction, they're same. Only thing, the phase components in the reaction, they are different. Say for example, Fe2SiO4 plus Mg2Si2O6 is equal to Mg2SiO4 plus Fe2Si2O6. Now you see here, this is olivine and this is also olivine, although there are 2 phase components of olivine, but the phase is the same. And here you have enstatite and you have ferrocyanide, and they are part of a solid solution of the phase orthopyroxene. So here you have olivine and you have orthopyroxene. Here also you have olivine and you have orthopyroxene. Only thing that the phase components undergo an exchange. Here it's exchange of MgFe between olivine and orthopyroxene. So there are 3 types of reaction in fluid-free reactions. One is polymorphic transformations, phase breakdown reactions where the phases on either side of the reaction are different, and then you have exchange reactions where the phases on either side of the reaction is one and the same, but the phase components are different. Now, all these reactions may happen simultaneously, or they can happen sequentially when the rock passes through a changing pressure temperature condition. You always get the end product. Unless you get zoned minerals, you always get the end product. Chemical thermodynamics, equilibrium chemical thermodynamics is path independent. So it doesn't depend on the path. So from here to Tikka's shop, I can go in many ways, right? So it's path independent. Chemical thermodynamics tells you, perfect chemical thermodynamics tells you that from here, Chotu's shop there, tea shop. That's all. These are the 2 places. It's path independent. It's not so with disequilibrium thermodynamics. Disequilibrium thermodynamics is path dependent. But you can apply equilibrium thermodynamics to find out PT paths, but that is a different issue altogether. So we have understood a little bit about fluid-free reactions. So you have polymorphic transformations, you have phase breakdown reactions, and you have exchange reactions. So when a rock changes its pressure temperature condition and tries to attain, these reactions operate along the path at the same time or in sequence. So this all happens together. Now we come to fluid-bearing reactions. So there are many types of fluid-bearing reactions. there are many types of fluid-bearing reactions. Say, for example, some of the ones that you have studied. Now, I will tell you a little bit about the fluids before I start the discussion. Normally, fluids are very complex. Fluids are very complex. So, the typical fluid that is present that we can deal with, and possibly 99% of the processes involve these components, are C, O, and H. C, O, and H, they fall into this. Now, except that when you take this as a system, if you take this as the fluid component, we'll come to that in a great detail later on. But for the moment, if you take the COH system for the fluid, you must remember that for C, you can have graphite and you can have diamond. Both of them also fall in this chemical system COH, graphite and diamond. Otherwise, the main fluid components are CO2, CO, CH4, H2, O2, and H2O. These are the dominant fluid components in the crust and the mantle. You see, you can say, sir, is that all? I said, no, it's not all. All the fluids that occur in organic chemistry, COH system, comes here. Alkanes, alkenes, alcohol, everything, all of them, benzene, all of them, acetic acid, name them, and they come under this system COH. But for the pressure temperature conditions that we deal with in the crust, we don't deal with surface processes. We don't deal with 25 degrees centigrade. Metamorphism essentially starts around 450, 500 degrees centigrade and up, and then goes up temperature. Those alkanes, alkene, alkenes, all those things, they are not stable. They break down much earlier. So we have to deal with the fluid which has these components for the pressure temperature conditions that prevail in the crust as well as in the mantle. But there are fluids where, for example, there is nitrogen involved. These have been detected. In the fluid inclusions, nitrogen have been detected, and then the system becomes bigger. Also, you get systems involving fluorine, involving bromine, or it's called halogens. So there can be more complex fluids. But for us, generally, we would deal with the COH. We will generally deal with the COH fluid. We will generally deal with the COH fluid, where mostly, as experiments show, CO2, H2O are the dominant components. Also, oxygen is very, very important. So, remember, when I am saying COH system fluids, I'm not saying whether fluid present system or fluid absent system. That we will do later on, once we are through with what we are discussing now. But the point is, most metamorphic fluids are in the system COH. Right? That is the system that we will be dealing with. We will talk about the COH fluid a little later in great detail. Fluids can coexist with graphite and at very high pressures. Where graphite tends to diamond, the fluid can be in equilibrium with diamond, or at the graphite diamond boundary, you can have fluids at the graphite diamond boundary. So it can be managed, it can be thermodynamically managed. But metamorphic fluids, very, very large, disproportionately large part, is essentially COH fluid. Nitrogenous and brine fluids are only in very special cases. Another fluid that I have not been able to talk to you was sulfurous fluids involving sulfur. Now these reactions, there are hundreds of fluid reactions, hundreds of fluid-bearing reactions. There's limitless, it's no use telling anything about the minerals. There are a tremendous number of such reactions. But just to give you an overall structure, Say for example, muscovite breaks down to corundum plus K-feldspar plus H2O. How does this work? KAl2, AlSi3, O10, OH twice, that's muscovite, breaks down to Al2O3 plus KAlSi3O8 plus H2O. Now you see the reaction is balanced. You have 1 potassium, aluminium 2 plus 1, 3, 2 plus 1, 3, silicon 3, silicon 3, hydrogen, H2, H2O is here, and you have 10 plus H2O, 1 oxygen is gone, so you have 11 oxygen. So total is 12 oxygen, and here you will see 8 plus 3, 11 plus 1, 12 oxygens. This is a balanced reaction. This is muscovite breaking down to corundum plus K-feldspar plus H2O. Another reaction that you might have studied, if you add plus SiO2 here and plus SiO2 here on both sides, then you get Kal2, AlSi3, O10 OH whole twice plus SiO2 quarts is equal to Al2SiO5 plus KAlSi3O8 plus H2O. Now I will tell you a little bit about H2O. Now this reaction involves H2O because it's a fluid building reaction. Because H2O is balanced with the structural water of muscovite. But when I say H2O, I have not said whether H2O exists as a fluid, whether it's a fluid present situation or a fluid absent situation. I have said nothing. What I said, in order to balance the reaction, H2O has to be added to this. But your fluid could be in the COH system. But this reaction only allows you to incorporate the H2O component of the fluid. That's all. This reaction, in order to balance the structural hydrogen, you have to have H2O for balancing. That means this H2O fluid component, H2O, CO2, CO, CH4, H2, O2, all this, you have balanced it with H2O. Now you see here, the complications that arise, H2O is equal to half O2. If you replace H2O by half O2 plus H2, you see that? Then of course, H2O is equal to half O2 plus H2O. You could write instead of H2O, you could have also put this as this. Right? So it would have liberated oxygen plus H2O. You could have written it in other ways also. But what is important here is to tell you that H2O is required to balance structural water of muscovite. That's all. It does not mean that the fluid has no CO2. It does not mean the fluid doesn't have H2. It does not tell you whether the fluid was present metamorphism or whether it was fluid absent metamorphism. It tells you nothing at all. Nothing at all. It just says, I have included H2O to balance the structural weight, because all reactions have to be stoichiometrically balanced. That's all. As I said, I could have written the reaction in a different way by replacing H2O by this 2. Then you don't have H2O in the fluid. So don't look at these reactions in a very, in a very restrictive way. There is flexibility. Have you understood? There is a lot of flexibility that you can introduce. So don't have a very fixed idea as, it has to be H2. No, it could be H2 plus half O2. And these two also are part of the fluid component. These two are also part of the fluid component. So this is just about the fluid component that is necessary. That's about it. It's a minimum requirement. Similarly, so these are called, as written in this way, these are called as written, it's called dehydration reaction. Dehydration. That means the muscovite has liberated H2O. Liberated H2O within inverted commas. Could have liberated a half O2 and H2. Right? That is what it is. And what is hydration reaction? Is the reverse, where aluminosilicate plus K feldspar, by introducing H2O, you can bring it, you can stabilize muscovite at a particular pressure temperature condition. Right? So, what I will suggest to you, these are, you remember one thing, when you involve fluid bearing reactions, they are only to balance structural water here. Somewhere it's carbon dioxide. That's all. It is referring to a component of a fluid phase. Whether that fluid phase exists as a phase or it does not exist as a phase, that's a completely different issue. How many components that fluid has is a different issue. Similarly, we can also have another type of reaction. So you have hydration and rehydration reactions. This is one type of reaction. Say, for example, you have heard about this reaction. Calcium carbonate, CaCO3 plus SiO2 is equal to CaSiO3 plus CO2. Read this reaction. Calcite plus quartz is equal to wollastonite plus CO2 as the vapor phase. Again, CO2 is merely here to balance CO3. Have you understood? To account for CO2 here, which is left over after you make this wollastonite. So it's referring to the CO2 component of a fluid. CO2 component of a fluid. That's all. That's merely, that is all. But also you have C plus O2 is equal to CO2. But then you would require, or maybe I can, but carbon is not here and diamond is not here. I can write CO2 is equal to CO plus half O2. Would do. CO plus half O2. So instead of CO2, I could write CO plus half O2. So again I am dealing with CO plus half O2. Do you understand? So one can do it this way. So CO2 essentially comes in to balance for the carbon dioxide. That's about it. Nothing less, nothing more. Again, this is a decarbonation reaction because carbon dioxide comes out. This is a decarbonation reaction. If the reaction went this way, it's a carbonation reaction. Right? And then you could have a reaction written differently. Say, for example, I just wrote one. 5 dolomite plus 8 quartz plus H2O is equal to tremolite plus 3 calcite plus CO2. In other words, if I write the formula, 5 CaMg CO3 whole twice plus 8 SiO2 plus H2O is equal to tremolite Ca2 Mg5 Si8 O22 OH whole twice plus 3Ca CO3 plus 7 CO2 plus 7 CO2. So this is a balanced reaction. So this means dolomite reacted with quartz to form tremolite plus calcite. If this was done, then H2O would be consumed and CO2 would be liberated. H2O would be consumed and CO2 will be liberated. The H2O that is available would be consumed and CO2 will be produced in the fluid. The fluid is COH. The fluid is COH. Have you understood? The fluid is COH. So if the reaction goes this way, in this direction, then dolomite plus quartz would react with H2O to produce tremolite plus calcite and liberate carbon dioxide. So going this way, it would act as a H2O sink. Have you understood? It would act as a H2O sink because it consumes H2O, and because it consumes, it stabilizes OH2. Here, dolomite does not contain H2O, quartz does not contain H2O. This H2O is taken in to produce OH twice, structural water in tremolite, and then calcium carbonate needs to be balanced, so you have 7 CO2. So H2O is consumed, CO2 is liberated. So, but all this is happening within a fluid phase. It is not that there is a separate H2O fluid phase and a separate CO2 fluid phase. No, it's all within the fluid. We will come to these discussions after we finish the thermodynamics part, and they're very exciting discussions, very interesting discussions. H2O acting as a sink, carbon dioxide is being liberated. So the fluid, if it goes like this, tremolite plus quartz gives you dolomite plus quartz gives you tremolite plus calcite, then it is H2O consuming, CO2 liberating. So H2O-CO2 ratio in the fluid is changing because it is decreasing H2O content and adding CO2. So the composition of the COH fluid phase is changing because of the reaction. Have you understood? It is also possible that you can have a reaction A is equal to B plus MH2O plus NCO2. This is also possible, that you have a set of reactants that produces another product and liberates H2O and CO2 in some molar ratio. Also possible. We will talk about them when we are talking of metamorphism of serraceous dolomites. But it is what I am trying to impress upon you is that when you write muscovite gives you quartz, you don't mean that your fluid contains only H2O. It does not mean. It means for balancing the structural water of muscovite, you had to use H2O, which is also a component of the sewage fluid. For the wollastonite reaction, you had to bring in CO2 as a fluid component to balance for CO2 held up in calcite. Here, you produce CO2 and you produce H2O. If the reverse reaction happened, tremolite plus calcite gave you dolomite plus quartz, then this reaction, then if you had the reverse reaction going, then CO2 would become a sink to produce dolomite. CO2 will become a sink to produce dolomite, and because tremolite is breaking down, H2O will be released. Because that H2O at that pressure temperature cannot be accommodated in any other mineral. So it can be all very complex. So what I am trying to impress, there are different types of fluid-bearing reactions, and their importance we will soon find out. But the important point to note here, that you are taking a component of fluid. This is not the fluid, just a part of it. You are taking that to balance the reaction. That's your primary aim. There is another type of reaction, and it is a very important type of reaction. This is called oxidation reaction. And the most famous one here is Fe3O4 is equal to Fe2O3. This you know is hematite, and this you know is magnetite. So if you balance for iron 3 and 2, so you will have 8 oxygen here and 9 oxygen here, so it's plus half O2. This is also a fluid species. We will talk about them if possible. If I get time, I will talk about them. These are called buffer reactions. I will tell you what they mean. These are called, this is called an HM buffer. HM buffer reaction. Similarly, say for example, another famous oxidation. These only involve the oxidation. Again, a fluid compound. It does not mean that it is oxygen fluid. No, it doesn't mean. It means that oxygen is required to balance the reaction, and that oxygen is a component of a fluid phase COH, or could be a larger component. Then, for example, you have SiO2 plus Fe2SiO4 is equal to, you can write a reaction like Fe3O4 plus SiO2 is equal to Fe2SiO4. Fe2SiO4. So what is it? So you multiply this iron by 3, 3 into 2, 6, and this one by 3. So iron is balanced. And you can see you have 3 silicon, so it should be 3 SiO2. Right? So it's 2 magnetite plus quartz gives you firelight. But if you look at oxygen, on the left hand side, you have 8 oxygen. Here you have 3 into 2, 6 oxygen, that is 14 on the left hand side. And on the right hand side, it is 12 oxygen. So there is an oxygen left. So this is called plus O2. So this is another oxidation reaction. It's a very famous oxidation reaction. It's called quartz. Okay. This is quartz, firelight or olivine, and magnetite. So it's called QFM buffer. Why buffer? We will talk about it. Quartz, firelight, magnetite buffer. There are many such buffer reactions. Nickel plus oxygen is equal to, say, Ni plus half O2 is equal to NiO. This is called NNO buffer. This is called NNO buffer. Nickel oxide buffer. So there are many of the reactions, but all of them involve O2. But again, I want to tell you, H2O is equal to H2 plus half O2. Now, therefore, if I add this and this up and remove oxygen, you will have a reaction H2 on one side, H2 on the other side. You see? But the thermodynamics won't change. Only thing, I can write instead of O2, I can write H2O and O2. On one side it will be H2, on other side it will be H2O. So that is how things go on. So essentially what you're doing is trying to track, using different reactions, trying to track the fluid component that is involved. Component. The fluid phase is COH. In what proportion you have COH2O, CO2, etc., that's a different issue. But what you can do is, you're trying to track these individual fluid compounds. So, this is all about the type of reactions that are available. Now, I told you so many reactions. And these are nothing compared to the number of reactions that are available. Thousands of reactions that operate in different bulk compositions over the range of pressure temperature conditions, either together or sequentially. So there is no end to it. You have to model it in the way you want it. Right? It depends on you, and I have told you for every system how you can find the Gibbs phase rule. I have told you how you find out the independent number of reactions. So for that equilibrium, you can find out what is the independent number of reactions, what are the possible reactions what are the reactions that are possible, independent reactions that are possible. You see, there are many reactions can be written. All reactions are not necessary. They overdo the system. You don't need it. They don't give you any data. So, for example, when a rock which was at a particular pressure temperature due to some tectonic processes, the physical environment, the intensive variables, the pressure and temperature, when they change, several of these reactions operate simultaneously so that new products are formed, mineral compositions change. New products formed means the mineralogy of the rock changes. When I say mineralogy, it means the modal amounts of minerals and the compositions of the minerals. Both together change. The composition of the mineral as well as the modal percent of the mineral, the volume percent of the mineral, that changes. And finally, if given enough time, the rock would equilibrate to give you that perfect assemblage that would give you the minimum free energy for the particular physical environment. And if you keep the composition same, then whether you go to Saturn or Neptune or Pluto or Mars, same rock at the same pressure temperature condition would give you the same minerals. Same mineralogy, meaning composition of minerals and production and mineralogy of minerals. It would give you the same. There will be no change wherever you go. But if you change the composition of the rock, then of course free energy minimization occurs over a different composition. And therefore the mineral assemblages that fall could be very diverse. And I told you in the first class, even a layered rock, which is layered in scales of centimeters, could behave very, very differently. Every layer could be a closed system. And they could give you widely different compositions of minerals, compositions of the minerals, modal mineralogy of the mineral. The whole thing would dramatically change. Right? We will now shift to thermobarometry. I will just introduce you a little bit, and maybe we could then work it out in the next lecture. The important part here is thermobarometry, but we have to work a little bit. So you have thermobarometry essentially involves estimating temperature and estimating pressure. These are the two fundamental necessities for us to find out pressure temperature conditions of rocks. That's the first thing you almost do for any rock if you're a metamorphic petrologist. Find out the temperature and pressure conditions. It is understandable, since you're trying to find out two intensive variables, you need two reactions or you need two equations. Very simple. Now, what happens is, if you take a temperature pressure diagram, T increasing, P increasing, then for example, any reaction that you draw that is there is something called the Clausius-Clapeyron slope, which is the delta SR of the reaction by delta VR of the reaction is dP by dt. This means this is dP and this is dt. So the del P by del P, or the slope of the reaction, is given by this relationship. That's important. In this, if delta VR is small or zero, if delta VR is small or zero, then this will be infinity. That means if delta VR is small or zero, this would mean the reaction is like this. Have you understood? If I write this as A, then A should be like this. Because if del VR is small, then this is infinity. So dP by dt obviously is equal to infinity. So if you have to find out temperature of a rock, you need such an equation to move, reaction to move parallel to itself. In pressure temperature space, it should move parallel to itself so you can estimate the temperature. Have you understood? This reaction, you can't estimate the pressure and the temperature independently. If you know the temperature, you will get the pressure. But for this reaction, if you get an ideally this, then you get the temperature independent of the pressure. That's called a geothermometer. And if delta VR is greater than delta 0, and we label this as reaction B, so the volume change of reaction is very large compared to the entropy change, then such a reaction would have a slope like this, because the slope would be 0. Because if the delta VR is very big, delta SR is small, then the resultant reaction would be parallel to the pressure, would be parallel to the this would be where dP by this is equal to 0, and for this dP by dt is equal to infinity. So you will have a reaction parallel to the temperature axis, and if you do so, then if there is a way to shift the reaction in pressure temperature space, we will see how it is done. If you can shift the reaction in pressure temperature space, then you can find out what is the pressure of that particular assemblage. Have you understood? So essentially, thermobarometers are to find out temperature pressure condition. Temperature is found out where the Clausius-Clapeyron slope of an equation is infinity, but dP by dt is equal to infinity. And pressures are determined by reactions of this type, where del P by del T is equal to 0. And this is where the intersection of these two should give you the pressure temperature condition that you desire for a particular equilibrium condition. This is the basic fundamental thing that is necessary for thermobarometry. But I think I don't have a lot of time now. What I will do is in the next class, we will talk a lot on thermobarometry for the 7 classes, and then we go on to computing fluid speciation in COH system, and then we go over to more or less classical progressive metamorphism of siliceous dolomites, amphibolites, and other things. But we finish basic logic of doing metamorphic phase equilibrium. Right? Thank you.